Okay, good afternoon, everybody. Hope everybody's doing okay. Okay, good. Um, Good afternoon. Okay, so we can go ahead and start the class. You all got my message about postponing quiz number 4 for Tuesday. I just wanted you to have enough time to look at the solutions as well that I will post tomorrow morning. Okay. Okay. So um, before I forget, let me mention uh, an item to you. Now, in all my classes, I always do a mid-semester survey of the class. So this is pretty much exactly the same questions that you have at the end of the class. Right? So at the end of the class, you have a survey that you fill out. I do the same thing at the midpoint of the semester, and this is mainly to get feedback on how I am doing in the class. Um, are you getting what are you getting what you paid for? Are you um, is what I'm doing working for you, or would you like me to change something? And if I am able to change it, I'm very happy to do that. Okay. So give me your feedback. I'll make that survey um, available to you today, right after this class. And you have till Sunday midnight to complete the survey. Okay. Good. Um, So let us continue with the new topic here. Oh, sorry, I haven't shared my screen with you. Okay, we have a chat window. Okay, good. How is the lab working out for you so far? Okay. Again, please let me know if there are any problems with the lab. I'm not teaching. Well, I'm not. I'm only managing the labs this semester because we don't. Anyway, that's a long story. So, I'm only managing the labs, and that's why I introduced the first lab, the material for the lab, and then I have my TAs run the lab. So, if there are any problems with the TAs or the lab itself, please let me know. Please let me know. Okay. Okay. Good. Um, Now, the next topic uh, in our roadmap from a dynamic system to a controlled dynamic system is stability analysis. Um, so, stability is important because uh, when we have a system that we want to control, let's say an airplane, a helicopter, an elevator, any dynamic system, if you want to control that system to perform the way you want it to perform, you have to design a controller for it. So before you design a controller, you have to do certain analysis on that system. The first one is the mathematical model, then the transfer function. So that's what we did in step one, the transfer function. Now, the transfer function allows us to ID the system. Is it a first order system? Is it a second order system? Um, then we can also look at the time response of that system. What happens if I put a unit step input into a first order system? How does that behave? What if I put a step input into a second order system? How does it behave? Okay, so things like that. Okay, um, what else? So chapter 5 Chapter 5 was taking a multi-block system and determining what from that multi-block system. Can someone tell me real quickly what we did in chapter 5? Anybody at all? Well, we had the block diagram. The block diagram represented how the multiple transfer functions interacted with each other, right? Correct. Exactly right. We determined the equivalent transfer function, the equivalent transfer function of that multi-block system, right? That's what we did. So if you look at the examples that we did last class, if you have these multiple blocks, then the equivalent transfer function is this. These multiple blocks, that's the equivalent transfer function. If you have multiple blocks arranged in this form, then the equivalent transfer function is that. So what does that do for you? From the multiple blocks, you get one total transfer function. That's why we called it the total transfer function, right? T. We called it the total transfer function. Again, this is multiple blocks, right? You have a transfer function, then you have the unity feedback. That's also a transfer function. Unity is also a transfer function. And we determined the equivalent transfer function by moving blocks or recognizing one of the three cascade parallel feedback, and then determined our total transfer function. So this total transfer function is the equivalent of this multi-block transfer function. So everybody sees that? Again, here we were able to determine a total transfer function between the input R and the output C. Okay, so that's going to be important for the next chapter, which is stability. Now, um, okay, so let me just say this. The stability of a physical system, of a dynamic system. If we have a static system, that static system is not moving, so there's no question about stability. Stability only comes in when you have a dynamic system. And when you put an input into that dynamic system, if its output is stable, then you have a stable system. So stability comes in three flavors: stable, marginally stable, and unstable. So what does stable mean? So stable means that let me show you this physical representation of stable. Okay, so this is asymptotically stable. I'll get to stable in a minute, but let me just let me let me define stable as this. Stable would be, let's say we have a surface and we have a car, okay, and then you exert someone puts a force on that car. That force can come from the engines, it could be coming from multiple people pushing the car. But what happens is that car will move from its initial state and it will go to a different state, right? Different position. And it will just stay there, right? So it goes from position 1 to position 2. So this is what I would call stable. Okay. Now, what happens if I were to, instead of a level plane, what happens if I were to tilt this ground? Okay. And then again, the same car you push it for a certain amount of time, okay, and it goes to a different location. Now, when you take the force away, what happens to the car? It's going to roll down. So that's an unstable state. Okay. So that's the concept of stable and unstable. Now, so what I've done for you is I've basically taken these three flavors of stability: stable, marginally stable, and unstable. These are the three flavors that we're going to be studying in this chapter. So unstable is what we just talked about, or if you look at um, an inverted trough, okay, and you have a little marble or a little sphere at the top of this trough, if you didn't do anything to that sphere, it would just stay there forever, right? It would be stable and stay there forever. However, if you perturb the position of this object by an infinitesimal small amount, what's going to happen? It will never return to its original state. It will just basically run away. Exactly like this thing here. If you leave the car here and take the forces away, what's going to happen is this car is going to roll down. So that's unstable. Marginally stable is if you have a constant oscillation of the system once you apply a force to it. So if you have a mass spring system, what happens to that mass if you apply a force F and compress the spring and let that force go away? What happens to that mass? Let's assume there's no friction. So you uh, you compress that spring for a certain amount, and then you let that mass go. What happens to that mass, do you think? Exactly. It's going to oscillate forever. Exactly right. Oscillate in a sinusoidal manner. It's going to oscillate forever. So that's what we call marginally stable. Okay. So in other words, if you took a trough, inverted that trough, and um, placed a sphere or a marble or whatever in that trough, and let's assume that that trough has no friction. It's a smooth, polished trough. If you perturb this marble or object by a certain amount, what's going to happen? It's just going to oscillate in that trough forever. Not realistic, but if we were able to achieve zero friction, it would basically oscillate in that trough forever. Okay. So does everybody understand what stable, marginally stable, and unstable system looks like? Okay. So let me show you what it looks like in a simulation. Okay. So let's say the transfer function. I'm going to say S is equal to TF of S. I'm going to say the transfer function G is 1 divided by S squared plus 10S plus, I don't know, I'm just completely making this up, 20. Second order transfer function, if I do a step input, if I put a step input into this transfer function G, what do I get? Oops. Okay, there you go. So put a step function into it, and it basically goes to a different location, just like your car, right? You pushed on this car and it went to a different location, and it's basically, it just goes to a different location and stays there. Now, what happens if I say g, a different transfer function, 1 divided by s squared plus 20. So I'm basically removing the damping, making this no friction. Hold on grid. Now, what do you think will happen if I were to put a step input into, aha, it just oscillates forever, right? Let's zoom in a little bit. There, it's oscillating forever. So that's a marginally stable system. And an unstable system, make this negative. New figure, step G, make that magenta. Aha, you see what happened? The system goes to infinity. Basically, it has run away. So that's an unstable system. So if you put a step input, if you put a bounded input into the system, and if the output is bounded, then we have a bounded input, bounded output, stable system. If you put a bounded input into a system and the system basically runs away, meaning the output of the system goes to plus or minus infinity, then we have an unstable system. Okay? Okay, so now I want to give you the tool to determine stability. How do you determine stability? Does anybody know if I have the transfer function, does anybody remember, or does anybody remember uh, what aspect, what characteristic of the transfer function indicates stability? So the system stability is determined by the poles of the total transfer function. Not the forward transfer function, not the feedback transfer function, but the total transfer function. So the poles of the transfer function, what are the poles of a transfer function? Anybody know what the poles of a transfer function are? We did this for exam 1.
Sorry, never mind. Sorry.
The the roots of what, Tony? There is a numerator and there's a denominator. The roots of what? Exactly, the roots of the denominator. What are the roots of the numerator? What are those? Those are the zeros, exactly. So the poles of the total transfer function. So remember, please, it's the total equivalent transfer function. Though that will determine if you have a unstable system, a marginally stable system, or a stable system. So if the poles are on the left-hand side, so if all the poles are on the left-hand side of the Gauss plane, then you have a stable system. If you have a pair of poles on the imaginary axis, you have a marginally stable system. And if you have any pole on the right hand side, that becomes an unstable system. So the rightmost pole determines the system stability. So, in other words, you can have a million poles on the left hand side. And if you have a single pole on the right hand side, that single pole will determine the stability of the system. You can have a million poles on the left hand side, but if you have two poles on the imaginary axis, then those are the two rightmost poles, and they make the system marginally stable. And again, you can have a million poles on the left. If you have a single pole on the right, that makes the system unstable. Okay, so let's look at our example again. Remember the original example was this, right? And when I did a step input, was that stable or unstable? Do you remember? Unstable. No, it was stable. Exactly right. It was stable. And how do I know that? Well, if I say G is equal to that, if I do the pole, let me just do the pole of G. Okay, so the pole of G is at negative 7.2, negative 2.76. So the poles are on the left-hand Gauss plane, and therefore the system is stable. What about G being this? The poles are on the imaginary axis. And you remember what happened when I put a step input into this transfer function? What happened? Figure step G, make that blue, oscillations, right? And and the poles of that transfer function are on the pure imaginary axis. And then we looked at this transfer function, right? No, this one. What was this? Stable, marginally stable, or unstable? Well, let's look at the pole of G. Ah, positive and positive. So that means two positive poles makes it unstable. Okay, so the poles, the poles are the roots of the denominator of the total transfer function. So the roots of the denominator of the total transfer function determine the stability of the system. Now, roots means um, you have to solve for the roots of the denominator, right? So remember, G of S is numerator over denominator. So the roots of the denominator tells you whether you have a stable system, a marginally stable system, or an unstable system. Again, please remember this. Stable system, all the roots are to the left of the imaginary axis. Marginally stable system, you have the poles on the imaginary axis. You can have two or more poles on the imaginary axis. And unstable means that you have all the poles or at least one pole on the right hand side. Remember, the rightmost pole determines the system stability. Okay, so what happens if this is a complicated, let's say this is 1 divided by, uh, let's look at the example that we're going to do. Let's say this is 1 divided by s to the power of 4 plus 3s cubed plus 2s squared plus 4. So you cannot manually calculate the poles of this fourth order transfer function, right? You would need MATLAB or some other analytical tool to calculate the poles of the transfer function. So instead of calculating the poles of the transfer function, there is a method called the Routh-Hurwitz method to determine system stability. And let me show you how that works. So for the Routh-Hurwitz method, here's my checklist. Always first find the total transfer function. Now, what is finding the total transfer function? It's what we did in chapter 5. So you have a multi-block system. You have to determine the total equivalent transfer function. Okay. Once you have the total transfer function, extract the denominator of the total transfer function. Um, Write out the denominator without any vanishing exponents on S. I'll explain that in a minute. And then create the RHC table. The RHC table will tell you whether you have a marginally stable system or you have an unstable system or if you have a stable system. So stable, unstable, and marginally stable. That's what the RHC table will tell you. Okay. Okay, so let's look at an example. Um, 1 over this polynomial that we have at the bottom. Okay, a fourth order polynomial. So practically impossible to determine the roots of that polynomial. Usually anything higher than 2, it's very difficult to determine the roots. Okay. So how does this RHC table work? Let me okay. So this is how it works. So the first thing that you would do is look for any vanishing S exponents. So you have S4, S3, S2, S, and S to the power of 0. So there are no vanishing exponents. Okay? No vanishing exponents. So we have 2S to the power of 4 plus S cubed plus 3S squared plus 5S plus 10. Okay? Now what we do is we start off, this is the RHC table. We start out with the highest exponent in S. So that's S to the power of 4, S cubed, S squared, S to the power of 1, and S to the power of 0. Okay, so for the first row, you take the even you take the first, well, s to the power of 4, you put the 2 over here. That's the same 2. Then you skip the next one, go to the s squared term, which is 3. Then you skip the 5s and go to 10. This is just a method, so just follow me on this method. Okay, so s to the power of 4, because that's the highest exponent, then s to the power of 4, 3, 2, 1, 0. That's your first column. Second column, take x to the power of 4, and which coefficient here is s to the power of 4? That's 2. Okay, 2, skip 1, go to 3. So basically, only take the even coefficients. Now, for s to the power of s cubed, you have 1, 1. Then you skip s cubed. No, sorry. S cubed is 1, right? Then you skip s squared and go to 5. Then you skip 10 and go to the next one, which is 0. Okay, so now we need to pay attention here. This is how you would read it. 2s to the power of 4 plus 1s cubed plus 3s squared plus 5s. So basically the first two rows contain all the coefficients of the denominator polynomial of the total transfer function. Is that clear to everyone? Okay, so now how do we do this? Um, we call this the pivot. Okay. Um, we take the negative determinant of this matrix here. Take the negative determinant. So what is the negative determinant of this 2 by 2 matrix? You all remember the determinant, right? A, B, C, D. That's A, D minus B, C. So the negative determinant is A, B, C, D. The negative determinant is BC, BC minus AD. Okay, so let's go ahead and take the determinant of this matrix here, the negative determinant. So the negative determinant is 3 minus 10. 3 minus 10 is negative 7. Negative 7 divided by 1, that makes it negative 7. Okay, then we move over one column to the 10, 1, 10, 0. So the negative determinant of that is 10. 10 divided by the pivot, that's I get 10. And that's 0. Okay, then we take the two rows above to determine the next entry. So again, this becomes my new pivot. This becomes my new pivot. Okay. So what is the negative determinant of this matrix here? That matrix. So that's minus 7 times 5, negative 35. Negative 35 minus 10 is negative 45. Negative 45 divided by negative 7. Negative 45 divided by negative 7, that's 45 over 7. 45 over 7. You skip the next column and use the 1 negative 7 0 0. Its negative determinant is 0. 0 divided by the 0 divided by negative 7, the pivot element, is 0. Okay? Then for this row here, you basically take the two rows above it. Okay? So 45 over 7 multiplied by 10 minus 1 times negative 7 times 0. So that's 0. So 45 times 7 multiplied by 10 divided by 45 over 7, that makes it 10, right? 0, 0. So we have now just completed our first our first RHC table. So it's pretty straightforward if you just follow the rules. So write out the coefficients based on the highest order of the denominator polynomial of the transfer function. S to the power of 4, 3, 2, 1, 0. Okay, now how do you fill out the entries? Well, you start off with the highest coefficient, s to the power of 4, 2, skip the next one, 3, skip the next one, 10, 2, 3, 10. S3, same way, 1 plus 3s squared, so that is 2, 1, 3, 5, 2, 1, 3, 5, 10. Okay, how did you get 10 in the S2 row? Okay, so 10 in the S2 row is, wait a second, how did I get that? Okay, so I have 3 minus 10 is negative 7 divided by 1. And then negative 7. Oh, yeah. That is 1 times 10 minus 2 times 0. So that's 10. 10 divided by 1 gives me 10. So that's correct. Bosco, very good. Okay. So there's the RHC table. The next thing that you have to do is check for sign changes in the first column. Okay, so the number of sign changes in the first column will determine the number of poles on the right-hand side. That's the beauty of this methodology. Okay, so again, how many sign changes do I have? So let me write this out in red. Number of sign changes in first column is equal to the number of poles, right-hand side poles, number of right-hand side poles. Oh my God. It took it too far. The number of right-hand side poles. Okay. Okay, So let's look at the number of sign changes in the first column. I have one sign change from 1 to -7, and then I have another sign change from -7 to 45 over 7. So this particular problem, this particular transfer function has two sign changes. Two sign changes, therefore two poles, right hand side, therefore this system is unstable. Okay. Let's quickly verify that in MATLAB. Again, I encourage you to verify your work in MATLAB. Use MATLAB to verify your work. So let's write this out. Okay, so G is equal to 1 divided by 2s to the power of 4 plus s cubed plus 3s squared plus 5s plus 10. Okay, now if I do a poll on G, see, these are the two right-hand side poles. It's a s to the power of 4, so it has four poles. So two poles are on the right, two poles are on the left. Is that clear to everyone? Okay. Now, the RHC method doesn't tell you uh, what the numerical value of the poles are. It doesn't tell you that. All it tells you is that there are two poles on the right-hand side. So if there are two poles on the right-hand side, then the total number of poles must equal 4, therefore two poles on the left-hand side. So again, if you were to draw it out, so two poles on the right-hand side, and therefore two poles on the left-hand side. Now, these two poles could be on the real axis. These two poles could be on the real axis too. We don't know that. But from a stability point of view, we don't really care. All we care is, do we have any poles on the right-hand side? And that's what the RHC table tells you. Okay, good. Please feel free to interrupt me at any time if you have a question. Okay, so here I'm confused on that one. Okay, so what is it that you're confused about, Emir? Question, Emir? So in order for it to be stable, there has to be 0 right-hand poles. That is correct, Crystal. No right-hand poles whatsoever. If we have 4 poles, which one do we focus on? Okay. So in this chapter, we're not going to be focusing on any pole as such. All we're going to try and determine is, do we have any poles in the right-hand plane? If we even have a single pole on the right-hand plane, we know the system is unstable. Amir, is that clear? Is it only for determining unstable, marginally stable, or stable? That's exactly right. The RHC table will only tell you if the system is unstable, marginally stable, or stable. So if there are any poles on the right, it's automatically unstable. That is exactly right, Amir. Any poles on the right, the system becomes unstable. Now, again, I'm glad you asked that. You can have a million poles on the left, right? A million poles on the left, system is completely stable. But if you have a single pole, if the million and one pole is on the right, that whole system just became unstable. Emir, is that clear? Okay. Again, by the same token, you can have a million poles on the left, system is completely stable, and now you have two poles on the imaginary axis. So now that stable system just became marginally stable. Does that make sense to everyone? How can we tell if the system is marginally stable? Well, if you have poles on the imaginary axis, the system becomes marginally stable. Yes, and Tony, I'm going to get to that. That's a special case of the RHC table. I'm going to get to that in a little while. Okay, so hang in with me, and I will show you how the RHC table um, how the RHC table will tell you if the system is marginally stable. Okay, so let's look at another example. What do you notice in this example? There is a vanishing component. There is a vanishing x. No, sorry. There is a vanishing s component, right? So this is equal to 1 s cubed. Oops, sorry. Uh, s cubed plus 2s squared plus 0s plus 10. Okay. So remember my checklist, write out d of s without vanishing exponents on s. That's what I meant. So I've written it out without vanishing components. I have s cubed, s squared, s to the power of 1, and s to the power of 0. Okay, so now I'm ready to um, actually let me make sure that I don't make a mistake. Okay, so I start off with s to the power of 3. Write this out properly. I start out with s cubed, s squared, s to the power of 1, and s to the power of 0. Okay, so s cubed, 1. I skip the next one, go to 0. I skip the next one, go to 0. Okay, s squared is 2. I skip the next one, I go to 10. And 10, I skip the next one, I go to 0. So you can pad the denominator polynomial with as many zeros as you want. Okay, now I'm ready to, is there always 3 rows? Crystal, what do you mean by is there always 3 rows? There are 4 rows here. Oh, is that what you mean, Crystal? That is there always 3 columns? No, not necessarily. In this example, oh, okay. In this example, we also had 3 columns, but no. The number of columns depends upon how many coefficients you have in the denominator polynomial. Okay. Okay, so let's look at the RHC table for this total transfer function. So that is 2 times 0, the negative determinant of this matrix here. The negative determinant of this matrix, where this is the pivot. So what is the negative determinant of this matrix? Can someone tell me? negative 10, correct, divided by the pivot 2, that gives it negative 5. Okay? Then I skip this column and go to the next one. So, so the first column stays the same. I skip the next column and go to here. What is the determinant of that matrix? 1, 0, 2, 0. The determinant is 0. Exactly right. Very good. 0 divided by 2, that is 0. And the next one is also going to be 0. Because we can add as many zeros as we want, right? Without changing anything. So skip the next this column here and go to this one here. The determinant is still 0. Okay. So far so good. Then we look at completing the last row. So to complete the last row, to complete the last row, look at the two rows above it. So we have, there's your two rows above the last row, right? The negative determinant, that's negative 5 times 10, that's negative 50. Negative 50 divided by negative 5 is positive 10. Positive 10. 0, 0. Okay, so let me insert a little space here. Can you do that? One, oh, okay, one more time. Okay, so we're going to go to, you understand how I got the row for s cubed and s squared, Emir? Okay, good. Now the S1 row, take the two rows above it, right? So the two rows above it is 1, 0, 2, 10. The negative determinant of 1, 0, 2, 10 is 2 times 0 minus 10. So the negative determinant is negative 10. Negative 10 divided by the pivot. So the pivot element is always the bottom left corner element of the first 2 by 2. So negative 10 divided by 2, that's negative 5. Okay. Then for this row, I skip this column. The pivot on the last one was negative 5. Yes, the pivot on the last one is negative 5. That is correct. It's always the left bottom element becomes the pivot. Good. Good. These are all great questions. I know you're seeing this all for the first time, so all your questions are valid. Please stop me at any time and ask me as many questions as you want. I'm always happy to answer those questions for you. Okay, so now we're done with the RHC table. We can get rid of these zeros. They don't really mean anything. So there's the RHC table. Now I look for sign changes in the first column. Okay, so I have a sign change here from 2 to negative 5, and then I have another sign change here from negative 5 to positive 10. Therefore, I have two sign changes. This system is unstable. Unstable system. Again, I can verify that with MATLAB. S cubed 2s squared plus 10. G is equal to s cubed plus 2s squared plus 10. How many poles do you expect this total transfer function to have? Anybody, how many poles do you expect this total transfer function to have? Exactly right. Three poles. Very good. Because it's a third order system, right? So if I do a pole on G, oops, what happened? Oh, this is not the transfer function, right? It's 1 over that. So G is equal to 1 divided by that. There are your three poles. Look at the first pole. The first pole is at negative 3.06, 0I. Look at the second two poles at 0.53 plus minus 1.73I. And that's what the RHC table predicted. Two sign changes, therefore, two. Um, therefore, two right-hand poles, right-hand side poles, and therefore the system is unstable. So for a control engineer, that in itself is a big thing, to be able to determine the stability, stable, marginally stable, or unstable. Any questions? Okay, so now we're going to come to the special cases. Okay, so remember this pivot, right? What is the pivot again? The pivot element is the bottom left corner of the 2 by 2 matrix. So in this case, it was 2, then it became negative 5, and so forth. For this case, it was 1, and then became negative 7. Does that make sense to everyone? Is that okay? Now, if the pivot element itself is 0, is there a problem? What problem do you see if the pivot element is 0? You're dividing by the pivot element, right? And therefore, division by 0 is illegal, is an illegal mathematical operation. Therefore, the Routh-Hurwitz table has a workaround for 0 pivot element. Replace the pivot element by a small epsilon, small positive epsilon. Once you replace the pivot element with a small positive epsilon, complete the RHC table using that epsilon and then check for sign changes. I'm going to give you an example. Okay, so there's an example. Immediately, what do you see immediately from this total transfer function? Yes? Exactly right. Thank you. We are missing an s squared. Not vanishing, yes, vanishing s exponent, missing an s squared. So I'm going to write it out with the vanishing. We have s cubed plus 0s squared minus 3s plus 2. Okay, so let's put some space here. Okay, So go ahead and start with the highest exponent, s cubed, s squared, s to the power of 1, s to the power of 0. S cubed is 1. Then I skip the next one, I go to negative 3. And then I skip 2 and I go to 0. S squared, I have 0, 0s squared. Skip the minus 3s and then I go to 2. Okay, here's a trick for you. Here's a trick for you. The total transfer function denominator polynomial must have all its coefficients in the first two rows of the RHC table. So you can check it, s cubed minus, okay, well, s cubed plus 0 times s squared minus 3 times s plus 2. So 1, 0, negative 3, 2. 1, 0, negative 3, positive 2. Okay, so this is my pivot, correct? The bottom left corner of the 2 by 2 matrix. So that's the pivot. Obviously, there is a problem. So I replace this with a small epsilon. Okay. Now, what do I have? Let me add some space here. Okay, forget that. Okay. Okay, so what do we have? What is the negative determinant of this matrix here? Negative 3 epsilon minus 2 divided by epsilon. Negative 3 minus 2 divided by epsilon. That's exactly right. Then let's move this a little bit over here. Okay. I skip this next column and I go to the next one here. So what is its negative determinant? 0. 0, right? And then what else do I have? I have more zeros, so I can skip this column here and go to that one. I just basically have zeros. Okay, so now we are at the last row. So for the last row, take the 2 rows above. Your 2 by 2 matrix is now this one here, right? Correct? So what is the negative determinant of this matrix here? The negative determinant of this matrix is 2 times this expression divided by this expression here. So that makes it 2, if I'm not mistaken, right? Does everybody see that? Okay. Now, epsilon, we replaced the 0 with a small positive epsilon. Okay, so if epsilon is positive, small and positive, what do you think is the sign of this expression? So we know that this is positive. So what happens? Okay, that's right. When epsilon is positive, small positive, then you have negative 3 multiplied by a small positive number, that's a negative number, divided by a negative number, that makes it a negative number divided by a positive number, that makes it a negative number. So that means that epsilon positive to a little negative number, and then you have a negative number, and so we have a positive number there. So there's a sign change. How many sign changes do I have in total? I have one and two sign changes. Two sign changes, that means two right-hand side poles, which means the system is unstable. Okay? Okay. Um, just a second. We can verify that in MATLAB by looking at the poles of this expression here. So s cubed minus 3s plus 2, g is equal to 1 divided by s cubed minus 3s plus 2 minus 3 into s plus 2 pole of g. One left-hand pole, two right-hand poles, positive 1, positive 1. Okay. I maybe it's not a good idea to go to the next material. So what I want to do is I want to make sure that you have understood the special case of a zero pivot and the non-general, the non-special or the general RHC table. Any questions? So again, if you have a zero pivot, replace the pivot with a small positive epsilon and carry out your RHC table. Then you're supposed to also replace it with a small negative epsilon and complete your RHC table. But what you get from step 2 and step 4, the conclusions are going to be identical. So do we keep adding columns until the first row hits it, until the first row hits a 0? Okay, Veronica had another question. Can you explain why the last row, first column is 2? Last row, first column is 2. Okay, yeah, good question. So, Anthony, I'll get to you in a minute. So, last row, again, so this is the negative determinant of this matrix here, right? So what is the negative determinant? Well, this multiplied by this minus 0. Veronica, do you see that? It's this multiplied by this minus 0. Divided by that, so 2 So you have 2 times this expression here, negative 3 epsilon minus 2 over epsilon, divided by the pivot, negative 3 epsilon minus 2 divided by epsilon, makes it 2. Any other questions? Anthony, do we keep adding columns until the first row hits a 0? Um, yeah, you could do that. Yeah, until the first row hits a 0. Yeah, you could add as many columns as you want as long as they're all zeros. Any other questions? Okay. Again, the RHC method is to characterize the stability only, not the pole location, not to tell you what the poles are, but only to characterize the stability of the system. So the first column, the sign changes in the first column of the RHC table tells you how many poles are on the right-hand side. Okay. Any other questions? Yeah. So this RHC table is really a remarkable way of quickly checking whether the system is stable, unstable, or marginally stable. And in next class, I'm going to show you the special case of zero row, the zero row case. So when you have when you have a row of all zeros, that's also possible. That's when you can have a marginally stable system. Okay.
Professor, I have a question, please. A little confused
Sure.
about when we going to check on negative or positive epsilon.
Ah, okay.
Thank you.
So for your purposes for this class, all you have to do is replace the 0 with a positive epsilon. Okay? Once you replace it with a positive epsilon, then yeah, steps 3 and 4 are redundant because the with a replacing the pivot element with a positive epsilon or replacing it with a negative epsilon, you get the same conclusion. So the person who asked me the question about the positive epsilon, is that a little clearer to you now, or did I not answer your question?
Thank you.
Did you get it?
Yes, sir.
Okay, great. So all you have to do is just replace it with a positive epsilon and then continue your RHC table. And if you find that you don't have any sign changes, you're good, your system is stable. But if there is going to be a sign change from a positive to a negative, that is indicative of the number of poles on the right-hand side. Okay. Any other questions? So what I would recommend that you do is please practice or look at the problems in the book that that cover the RHC table for the general non-special case and the RHC table for the special case of a zero pivot element. And the next class we'll look at the next special case of RHC tables where the whole row is zeros. Okay? Okay? So I'll go ahead and stop the share. Are there any other questions? Okay.